Welcome to Gauss's Law, Day 2. We're going to be deriving a few more of these electric field equations that we've got. So just as a reminder about some things to begin with, if an isolated conductor, solid conductor carries a charge, the charge resides on the surface. Right? If it's a conductor, the charges can move freely, and so the extra charge is going to move to the surface away from all the others, or it's going to try. The E field is zero everywhere inside the conductor, since all the charge is concentrated on the outside. And the electric field just outside a charged conductor is perpendicular to the surface and has the magnitude given by this, right? E is sigma over epsilon naught. What else? Okay, an irregularly shaped conductor, the surface charge density is greatest at locations where the radius of curvature is the smallest, right? So it points, things like that. That's why lightning rods, right? They have a point because that's where the charge is going to be the greatest, and that's going to attract the lightning bolt to hit that point. And then if you have a charge inside of a cavity of a conductor, it makes an equal but opposite charge reside on the inner surface of the conductor. So if I have some conducting shell, right, here's a shell. If I have a, plus 4 Coulomb charge there, then I'm going to have, 1, 2, 3, 4. I'm going to get the equal but opposite charge on the inner surface happening, which we've looked at a little bit already, but just as a reminder for some of these things. Okay, so let's get into these. Example 1. Okay, so we have a solid conducting sphere, has a net positive charge of plus 2q. So this is plus 2q. And then the conducting spherical shell has an inner radius b and outer radius c. So here's inner radius b, outer radius c, and a net charge of negative 4q. All right, so this is negative 4q. So overall, the overall charge here is negative 2q. And so let's take a look. We've got plus 2q. That means I'm going to get a plus and a plus, right, on opposite sides residing on the surface here. That means I'm going to attract negative and negative, right? 2 negatives there. Right? Now this overall has a net charge of negative 4q. That means I've got 1, 2 on that inner surface. Now I'm going to have negative, negative on the outside. So from far away, what you would see is just overall negative 2, which is what's on the surface of that outer spherical shell. All right, so we want to know inside of the solid sphere, what's the electric field inside the solid sphere? Well, Q enclosed is 0, and therefore the electric field is 0 inside of that shell, or inside of that sphere. For B now, between A and B, so from here to here, so here electric field is going to be 0. This is a graph down here of the electric field, so that'll be 0. A, now we're going away from here, and the enclosed, Q enclosed, is going to be plus 2. Plus 2q, whatever that is. And so the electric field is going to be k 2q, whatever that is, over r squared. And so the electric field is going to look something like this. It's going to be up here. It's going to be coming down. But it's going to hit B. It doesn't get all the way to 0 because by the time it gets here, it's not an infinite distance away. Right. And then from B to Z, from B to C, rather, mixing up my letters, I want to know within the walls of the spherical shell, from here to here, what is the net charge there? So if I draw this Gaussian surface, this imaginary dotted line, right, between the two, if I enclose here, well, I've got the negative 2 and the plus 2 canceling each other out. So in this region, Q enclosed is 0. And so the electric field is going to be 0 in that region. Right? And then for D, when I'm outside altogether, Q enclosed, the net charge is negative 2Q. And so the electric field is going to be K negative 2Q over R squared. And so that is going to look like this. It's a negative field, so it's below. And then it's going to go out. That shouldn't hit that line, but it's going to approach as it goes out that way. Doing this kind of thing, you're going to see stuff like this. You might even see a QQQ. So get used to doing this. It should look similar. It's like what we've done with gravitational fields. The difference here, again, is that now we have negative. With gravitational, we only had positive, but here we have negative electric fields. So again, we've got this thing where we've got these spheres, +2, +4. That means on the outside here, I'm going to get positive, positive. They go away to the outside. And then that means I'm going to get equal but opposite charge on the inside surface of this shell. So negative and negative there. But this has to have overall of +4. That means I need to put 6 positive charges around the outside of this to make up for these negatives that have collected on the inside surface there. All right, so now if I take 6 positives, the 2 negatives here, that adds up to overall of +4Q. And same kind of setup, we have A is the radius of this inner sphere, B is the inner radius of the outer shell, and C is the outer radius of the whole thing, the outer radius of the outer shell. And now we want to know inside of the solid sphere, in here, right? So if I draw a Gaussian surface here, that's like for letter A, Q enclosed is 0. So the electric field is 0 for radii less than A. And so that's just going to be this. Okay. Oh, sorry. This is an insulator. Since it's an insulator, sorry, this is evenly distributed throughout, and so it actually goes like this. Hi, what's up? Okay, so now, again, realizing now this is an insulator, not a conductor, so the charge is evenly distributed within. We've already looked at this, right? That is a straight line like that. Okay, and the electric field then between A and B, right, so outside of A, so in here, so the Q enclosed within this Gaussian surface is 0, sorry, not 0, plus 2Q. So the electric field is going to be K positive 2Q over R squared. And so it's going to be this kind of thing. Right? Again, going out. Enclosed in here between B and C, Q enclosed is 0. Right? If I'm going around, I have this positive 2, but the negative 2 collected on the inside surface here balances that out. So the Gaussian surface, this imaginary spherical surface that I draw in here, Q enclosed is 0, so the electric field then is also 0. For part D, going all the way outside, now I have +6. The overall net charge enclosed out here, if I draw this Gaussian surface, everything enclosed is +6. That means the electric field is going to be K plus 6Q over R squared. So that's going to look something like this. So this is 0 between B and C, and then it jumps up at the surface as you pass this collected charge on the outside, and so that's what the graph looks like for this setup. Okay, now we're going to take a look at deriving Gauss's law, or using Gauss's law to get an electric field for a line of charge. And so here are our parameters. We've got these two areas, right? So the Gaussian surface we're going to use, the imaginary surface, is a cylinder. Okay, and you can see it with the dotted lines here. It has a length of h, and it has this outside radius, which is kind of the outer wall of the cylinder, and these two. The flux through these two ends of the cylinder is going to be 0, because the electric field lines are going to be running parallel to that surface, or perpendicular to the surface vector. Okay, and so so let's take a look. The total area, right, is adding up all the area of the cylinder, so that's the two sides and the thing here. So the electric field lines do not penetrate A1 or A2, only A3. And so phi again is the surface integral of E dot dA, so that's EA cosine theta, equals Q enclosed over epsilon naught. And so these two, cosine 90 goes to 0, this sign is just 1. And so E times 2 pi RH, that's the area of the outer wall, equals Q enclosed over epsilon naught. Okay, so what we need to do now is find what is Q enclosed. Okay, so lambda is big Q over L, and that's equal to Q enclosed over H, right? H is the distance here. And so therefore Q enclosed is just lambda H. And so E equals 2 pi RH equals lambda H. So we divide both sides by the 2 pi RH, we get E equals lambda H over 2 pi RH epsilon naught. We simplify and we move things around. So we've got lambda over 2 pi epsilon naught R, which is also equal to 2k lambda over R. Okay. The interesting thing here is that the length of the Gaussian surface doesn't matter. What we find is this is independent of the length of this wire, or this line of charge. It's just how far away you are and what the surface, or what the linear charge density is. So here's example 3. You've got two long, thin cylindrical shells, radii R1 and R2. And so if you have, here's one thin cylindrical shell, and here is the other thin cylindrical shell. And we can imagine, right, they go like this. This inner surface is like that. And then here's the outer surface of this one, and then inside. Okay, so that's my attempt at drawing two cylindrical shells near each other, right? R1 and R2, with R1 less than R2. So let's do this. We'll say this is R1, that is R2, and this is the graph for the electric field. We'll see what this looks like. So when you're inside of R1, if I draw a Gaussian surface in here, right, question A is asking when little r is smaller than capital R. Capital R, again, is the fixed radius of the object itself. So it's thin, so what you see here as a thickness is actually not there, right, but I had to draw it. And so when we're inside of here, the enclosed charge, Q enclosed, is 0, so the electric field is 0, right, for part A. For part B, when you're between the two, E is equal to just 2k lambda over R. Okay, and so what does that look like? That also looks like this, right, because here if you go around, so our Gaussian surface here is a cylinder, right, a long cylinder. Enclosed within that cylinder, it has a charge density lambda, right? And so then the electric field is given by 2k lambda over R. And then C, if you draw a Gaussian surface out here, the enclosed charge here is 0, and so then the electric field here is also 0, and so anywhere outside of these at any radius, we have electric field of 0. Okay, now we're going to use Gauss's law to derive the electric field inside a cylindrical insulator of uniform volume charge density rho. Okay, uniform, that's going to be important here. The next section will be looking at non-uniform, but we'll cross that bridge when we get to it. And so being inside, we're going to be looking at little r less than big R. And so rho is big Q over V of the cylinder, or dq dV. Therefore, dq is rho dV. V is pi r squared h. I like to think of this as the area of the circle of the base, and then just multiply the area of the base by the height. And that's how you get the volume of a cylinder. And so dV dr is equal to 2 pi RH This is the derivative of volume with respect to radius. That's going to come in handy. dV is 2 pi RH dr, right? Distributing the dr to the other side. So when R is less than R, for Q enclosed, we have to add up all of the charge, right? Add up all the little pieces of charge, and what is dq? So we go down here, dq is equal to rho dV. So that we substitute dq rho dV, and dV is going to be this thing, right? So rho times 2 pi hr dr. Rho doesn't change, 2 pi h, none of those things change, so we bring those out. We're going from 0 to r, so to some radius which is less than big R. Ah! What is that? Man, I hate it when that happens. And since it's integral r dr, we end up with r squared over 2, substituting r. And so the 2's cancel out, it just becomes rho pi h r squared. This is how we find Q enclosed. Right? Q enclosed is important in Gauss's law because we're going to plug that in here. So EA is Q enclosed over epsilon naught. And so, A is 2 pi RH, because that's the area of our Gaussian surface. Because the Gaussian surface we're going to use here, obviously, is also a cylinder. And so the outer wall of the cylinder is going to be 2 pi RH. That's the area. So E is this expression, right? We divide this to the other side, and we simplify, and we end up with rho R over 2 epsilon naught. Okay. How about outside a cylindrical insulator? So here, all this is the same, right? Same as before, dV, 2 pi RH dr, dq is rho dV, all that stuff. For R bigger than R, then what we're doing is we're adding up all of the enclosed charge, right? And here we're going from 0 to big R, notice. Because when we're outside, what we're doing is we're just adding up all of this stuff. And so this ends up being just big R squared. Same as before, except now it's big R squared instead of R. Set up Gauss's law. E dot A is Q enclosed over epsilon naught. A again is 2 pi RH. And so now I get this, right? I divide both sides by 2 pi RH under here. So I get pi, and Q enclosed is rho pi HR squared. And simplify things, we end up with rho big R squared over 2 little r epsilon naught. Okay, so moving right along, now we're going to look at the electric field for a non-conducting sheet of charge. The idea, since it's a non-conducting sheet of charge, whatever the charge is, it's evenly distributed kind of throughout the interior of this sheet, whatever it might be. The Gaussian surface we're going to use is a cylinder again, except this time the area that matters is this area here on the end. Now this kind of outer wall of the cylinder, the rounded wall of the cylinder, the electric field passing through it, the flux, is 0. All right, so as far as phi is concerned, right, A1, A2, and A3 is that outer surface. That's 0. So these are the only two surfaces that matter, A1, the end here, and A2. And so phi is E times these two, and that's equal to Q enclosed over epsilon naught. Okay, so then how do we find Q enclosed? Now we need to find Q enclosed. So it's sigma is Q over A, Q enclosed over pi r squared. The area is a circle here, right? And so Q enclosed is sigma pi r squared. That makes sense. The surface charge density times the area charge density. And so we end up with 2e pi r squared. All right, that's what we got from the last thing. What we ended up with down here, right? This is 2e pi r squared. And then that's equal to Q enclosed over epsilon naught. Divide both sides by 2 pi r squared down below. The pi's, the r's cancel out, and you're just left with sigma over 2 epsilon naught. Notice the radius of the Gaussian surface doesn't matter. For a sheet of charge, it only matters, notice it doesn't even matter how far you are from this. Right? So the idea is that this is a large sheet, and all these lines are just going straight up. So no matter how far away you are, the electric field is going to be the same. Okay, example 4. Here you have a circular non-conducting hoop of radius r in the region of a space near a large non-conducting plate. Okay, so it's an insulator. The surface charge density is sigma. Find the flux through the hoop for each position shown. Express your answers in terms of sigma, r, and fundamental units. So remember, flux is E dot A, or EA cosine of theta. Given where these two are vectors, and here are the magnitudes times cosine of the angle between them. And so the first one, they are parallel to each other, and so it's 0. So in A, it's just E. Well, the flux is given by sigma over 2 epsilon naught. So we want to find the flux through the hoop for each position shown. And so the flux is going to be EA. E is given by sigma over 2 epsilon naught. And then A is given by pi r squared. So this is just sigma. That's not a sigma. Sigma pi r squared over 2 epsilon naught. For B, it's the same thing, except now it's at some angle. So sigma pi r squared over 2 epsilon naught cosine of 45. Okay. And then for C, the flux is 0 because the angle between them is 90 degrees and cosine of 90 is 0. So something like a free body diagram. It's not exactly a free body diagram because I have the theta in there. On a real free body diagram, I wouldn't put the angles or anything like that, but this is where we're going just to help us analyze this problem. So the mass, 2 times 10 to the negative 6th kilograms. Q is 50 times 10 to the negative 9th coulombs, and sigma, the surface charge density, is 2.5 times 10 to the negative 9th coulombs per square meter. And so now we want to find the angle of the thread. It's a non-conducting sheet. And so the electric field is given by sigma over 2 epsilon naught. And so the electric force is EQ, right? So sigma over 2 epsilon naught times the charge. If we plug those numbers in, we end up with 7.1 times 10 to the negative 6th newtons. Okay, so that tells me this. And then I can find the force of gravity, Fg, just mg. So this mass times 9.8. And that gives me 1.96, if I can write a 9, times 10 to the negative 6th. Times 9.8, and that gives, 1.96 times 10 to the negative 5th, that's just the answer. Okay, and so then if I make a triangle out of this, right, that's Fe, this is Mg, this is the tension, and so I'm looking for this angle. So tangent of theta is going to be opposite over adjacent, Fe over mg, so tan to the negative 1, inverse tangent, rather, of the electric force over the force due to gravity. And so if I take inverse tangent of this, you should get about 20 degrees.